Welcome to Sri Learning Academy. Let's simplify what is shared memory and message passing in interprocess communication. Up to this point, we have talked a lot about processes as independent entities. We learned that each process has its own memory space, its own state, and its own execution context. This isolation is very useful for stability and security, but it also creates a new challenge. In real systems, processes rarely work completely alone. They often need to cooperate, share data, or notify each other about events. This is where the idea of interprocess communication or IPC comes in. In simple terms, interprocess communication is the set of mechanisms that allows processes to talk to each other. You can think of it like people working in different rooms of the same building. Each person has their own room and cannot see what is happening in the other rooms directly. If they want to collaborate, they need some way to exchange information. They might talk through a phone, pass notes, or meet in a shared meeting room. IPC provides similar options for processes. There are many IPC techniques, and we will explore specific ones like pipes, message queues, and shared memory in upcoming topics. For now, the goal is to understand the two main approaches behind all IPC mechanisms. These are shared memory and message passing. Almost every IPC method you see later will fall into one of these categories or be built on top of them. Let us start by understanding the basic idea of shared memory. Normally, each process has its own private address space. One process cannot directly access the variables or data of another process. Shared memory changes this rule in a controlled way. In shared memory communication, the operating system creates a region of memory that is shared between two or more processes. All participating processes map this region into their address space. Once this is done, they can read and write data in that shared region as if it were their own memory. A good real life analogy is a whiteboard placed in a common office area. Multiple people can walk up to the whiteboard, write something, erase something, or read what others have written. The whiteboard is the shared memory. The people are the processes. The important point is that once the whiteboard is available, no middle person is needed to pass information. Everyone sees the same data directly. Now let us see how this works in an operating system context. Suppose process A produces some data and process B consumes that data. With shared memory, the operating system sets up a shared buffer in memory. Process A writes the data into this buffer. Process B reads the data from the same buffer. There's no need for the operating system to copy the data back and forth after the setup. This makes shared memory very fast, especially when large amounts of data are involved. For example, imagine a video processing application. One process reads raw video frames from disk. Another process applies filters to those frames. If they used message passing, every frame would need to be copied from one process to another. With shared memory, the frames can be placed in a shared region and both processes can access them directly. This reduces overhead and improves performance. However, shared memory comes with a serious responsibility. When multiple processes access the same memory region, coordination becomes critical. What if process A is writing data while process B is reading it at the same time? What if process B reads half updated data? These problems are known as synchronization issues. This is why shared memory is closely tied to concepts like critical sections, semaphores, mutexes, and monitors, which you will study later in process synchronization. In simple words, shared memory gives you speed, but you must handle synchronization carefully. The operating system usually helps with creating and managing the shared memory region, but it does not automatically protect you from logical errors. The processes themselves must agree on rules like who writes when, who reads when, and how conflicts are avoided. Now let us switch to the second major approach, message passing. As the name suggests, message passing involves processes communicating by sending and receiving messages. Instead of sharing memory directly, processes exchange data through the operating system. One process sends a message. The operating system delivers it to another process, either immediately or by storing it temporarily in some buffer. A simple analogy here is sending letters through a postal service. You write a letter, put it in an envelope, and hand it over to the post office. The post office takes responsibility for delivering it to the receiver. The sender and receiver do not share a notebook or whiteboard. They remain completely separate and communicate only through messages. In operating systems, message passing can be implemented in different ways. Messages can be sent directly from one process to another, or they can be sent to a mailbox or queue, which another process reads from. The operating system handles details like buffering, copying data, and sometimes even synchronization. Let us take a simple example. Suppose you have a client process and a server process. The client sends a request message asking for some service. The server receives the message, processes the request, and sends back a response message. This pattern is very common in operating systems and distributed systems. In fact, when processes run on different machines, shared memory is not possible at all. Message passing becomes the only option. One big advantage of message passing is safety. Since processes do not share memory, there is no risk of one process accidentally overwriting another process's data. The operating system acts as a mediator. This makes message passing easier to use correctly, especially for beginners or in complex systems. Another advantage is that message passing works naturally in distributed environments. Even on a single machine, it supports a clean separation between processes. This is one reason why microkernel based operating systems rely heavily on message passing. Many core services run as separate processes and communicate only through messages. However, message passing has a cost. Every message usually involves copying data from the sender's memory to kernel space and then to the receiver's memory. For small messages, this overhead is acceptable. For large data transfers, it can become expensive. This is why message passing is often slower than shared memory for high volume data exchange. There are also design choices within message passing. Communication can be blocking or non blocking. In blocking communication, the sender may wait until the message is received, or the receiver may wait until a message arrives. In non blocking communication, processes continue execution and check for messages later. These choices affect performance and program structure, and we will see concrete examples when we study message queues and pipes. Now let us compare shared memory and message passing directly to understand when each approach is preferred. Shared memory is typically faster because it avoids repeated data copying. It is well suited for large data transfers and high performance applications. However, it requires careful synchronization and is more error prone if not designed properly. Message passing, on the other hand, is easier to reason about. Processes are clearly separated. The operating system handles most of the complexity. It is safer and more flexible, especially when processes are distributed or when isolation is important. The trade off is performance overhead due to message copying and kernel involvement. Think of shared memory as two people working on the same document at the same time. It is fast and efficient, but they must coordinate carefully to avoid overwriting each other's work. Message passing is like emailing documents back and forth. It is slower, but there is less chance of confusion about who changed what. Modern operating systems often support both approaches because they solve different problems. Even within the same application, developers might use shared memory for fast data exchange and message passing for control signals or notifications. For example, one process might place data in shared memory and then send a small message to another process saying that the data is ready. As we move forward in this module, we will dive into specific IPC mechanisms like pipes, message queues, and shared memory in detail. Each of these will make much more sense now that you understand the two core philosophies behind IPC. Shared memory focuses on speed through direct access, while message passing focuses on safety and structure through control communication. That is it for this video. See you in the next one.